Happy Monday. We're going to dive back into this. Announcements. This is the second week, so we have an assignment due Wednesday. I'm thinking and really considering trying to make the next assignment due a week from today, just to make sure that as many people can get feedback ahead of the first exam as possible. I need to talk to my TA about that. He's been trying to make more assignments and fewer assignments, just so that it's a little bit more manageable with a few more due dates than have historically been the case. We will see what happens for that, but kind of worst case, expect that there might be a second assignment that to work on between Wednesday and Monday. We have to make a little bit of progress, though, to make sure that that's something that is completely feasible. So that puts our first exam a week from Friday. That seems like a while from now, but the important point is that you should expect a study guide for that by this Friday. So by Friday, you will have something to help you prepare for what is to come a week from Friday. Questions before we dive back in? All right, we're looking at our second finite automaton. This is the non-deterministic finite acceptor or non-deterministic finite automaton. I don't really care which of those the A stands for. I've heard both. I know both. So we're going to allow for non-determinism. What was that concept of non-determinism? Does anyone want to take a stab at explaining that concept for those of us who weren't here on Friday, or just to make sure that you have a good understanding of that concept of non-determinism?
It's basically when you have, like, for example, well, I'll just call them nodes. So one node and two edges, and it's not determined exactly what case for it can go to either one of the edges, basically.
Yeah. So for a particular vertex within a state machine, you can have multiple vertices of the same edge label going out of it. There's also the concept of guessing and checking, where if you're going to guess, you guess correctly. I don't know, that's probably my least favorite way of describing it. It was how it was described to me. That never really clicked with me. The way that really clicks with me is the concept of infinite parallelism, where you have unlimited computational resource. And so as you're writing a program, you can fork an unlimited number of children. You don't have to worry about RAM. You don't have to worry about dividing your CPU speed between all of those processes or assigning cores to them. You just have unlimited cores and unlimited RAM. So if you need to make 100 children, you can. If you need to make 10,000 children, you can. And none of those children will be any slower because of it. So we talked about three major differences between DFAs and NFAs. The first was that we allow a lambda transition or a teleportation between two states, which means we can create an edge between two states with no or an empty edge label. So we're just going to label it as lambda, but that means that we don't consume any input. No characters in the input string are consumed when we make that transition. Then, as mentioned, we can have multiple transitions out of a particular state that consume the same input label. And then finally, we don't need to specify every possible transition. It is okay for an NFA to be a partial function. We just need to make sure that we have all of the edge labels that are necessary in order to define acceptance. We don't have to completely define rejection, because if we don't lead to acceptance, then we will assume rejection. So if you find yourself at a state, you're at a particular symbol in the input, and you're trying to determine where should I go from here. If there is no such edge label, we just immediately reject. There is no path to acceptance, therefore we are done. So here is an image of one such NFA that contains all three of these. There's no particular value, I don't think, to this NFA. It's not doing anything useful, as you can tell, because there's no edge out of Q2. But it at least visualizes the fact that there is a lambda transition between Q0 and Q2. That means that at any time, for any reason, if we are in Q0, we can just teleport to Q2. without consuming anything in the input. You might even say we're in both Q0 and Q2 at the same time. In Q1, there are edges out, both to Q0 and Q2 on a 0. And finally, there is no edge defined out of Q2. So those are the three different differences. All three of them are embedded in this NFA. But other than that, it is exactly the same as a DFA. We still have final states, we still have edge labels. Those edge labels can only consume up to a single character in the input. I say up to because lambda transitions consume 0. Questions on this image or any of these differences?
So when we're talking about number 2, what does that mean in terms of like how it works? Does that mean it'll go to either one, or is there a more likelihood that it'll go to one than the other?
Think of it like forking a program. You're going to make 2 children. One of the children goes down the first path. One of the children goes down the second path.
Okay.
That might be the simplest way of explaining it. But yeah, if there are 2 paths, then it's a branch. If this was deterministic, we would have to search both of them.
Yeah.
But with non-determinism, they go down both at the same time.
Oh, I see.
Kind of like cracking a password where there is one password that is correct that is 6 characters. But we're going to now non-deterministically explore all possibilities of the first character at the same time. And then we would explore all possibilities of the second character for each possibility for the first character at the same time. And that cuts the running time down from exponential, where we have to search down every possible 6-character sequence, to linear based on the length of the password, because we have a ton of parallelism going on at the same time. And exploring that space only takes as long as typing those 6 characters. At the end of typing those 6 characters, each one of those 62 to the 6th forks all are typing a different password. But in the time it took to type 6 characters. So it's a very strange concept, but it's one that, when you think about it, is extremely interesting in terms of, if we could make such a program, if we could allow for such, this would be the strongest possible use of a computer. It just requires infinite computational resource, which, of course, we don't have. So why bother to study non-determinism at all? Might be the question you would ask. If we can't make a computer do this, why do we care to study it? First thing to note, computers are deterministic. Any algorithm that we write is deterministic. What value is there to non-determinism? This is where we take a bit of an aside and talk about one of the more complex topics from your algorithms course. For those of you who have taken algorithms, hopefully that's just about everybody, considering it as a prerequisite to the course. So there are lots of problems out there that have much easier non-deterministic solutions than deterministic solutions. You can imagine if you have infinite parallelism, that would make it very interesting and very simple to solve a lot of problems that are deterministically exponential. So first thing to note, soon we will see that we can convert between them. If we have an NFA, we can convert it to an equivalent DFA. As an example, anytime we have a search and backtrack algorithm, thoughts for optimizing them, we could just make the choice that is most likely to lead to the goal and explore that. That's how we've handled it deterministically. But if the path leads to failure, then we backtrack and look at the next most likely choice. And that's how we can optimize for this. Even though in the worst case, nothing changes, we can lead the average case closer and closer to the best case by, if we can find a way to determine what is most likely to lead to a solution. But non-determinism allows us to see how much of that work is required, because we see the depth of the equals solution. And that is the most work that it could possibly be, assuming that we could identify where the solution is from the beginning. So, of course, doing that instead of the actual worst case analysis of searching through everything. Well, let's talk about the biggest open problem in computer science. I don't know if this is true anymore, but for decades, it's been the biggest open problem in computer science. Who's familiar with the P versus NP problem? Who's at least heard of it before, P versus NP? Anyone know what it stands for? What does the P stand for? What does the NP stand for?
Polynomial versus non-polynomial.
It is not non-polynomial. It is polynomial, and the second P is, but the N is actually non-deterministically polynomial. So this is where non-determinism comes in to that problem, is we want to determine whether two classes of algorithms are actually equivalent. Whether something that can deterministically be solved in polynomial time, whether it can be solved non-deterministically. Exactly the other way around. Something that can non-deterministically be solved in polynomial time, whether there is a deterministic polynomial time solution. So take, for example, the cracking a password that we talked about. Since there is a polynomial time solution for cracking that password non-deterministically, is there a deterministic one? Is there a way for us to somehow, without searching for the password, end up with that? In this case, it's pretty obvious that there is not. But there is a class of algorithms called NP-complete for which we have polynomial time non-deterministic solutions. But we have never found a deterministic polynomial time solution. So you can imagine making a graph of these problems where, let's say, in this graph, we have vertices represent problems. Let's give you an example of one you've hopefully seen before. Are we familiar with the traveling salesman problem?
Yeah.
That is, given a graph, we want to start at a particular edge, start at a vertex, visit every other vertex in the graph and end up back where we started. But we want to minimize the total edge weight as we do that. So this would be like finding the best driving route between 10 US cities, starting in Spokane and ending up back in Spokane. Or we can say that it's 1,000 cities instead of 10 cities. It needs to scale. As the number of cities that we are looking at grows larger and larger, then the time that it takes us to find that optimal route grows exponentially. It becomes infeasible for the modern computer to be able to find a solution for it. So I'm going to label this the traveling salesman problem. The entirety of this vertex is the traveling salesman problem. But it turns out that there is another algorithm called the 3-SAT problem that we can convert from the traveling salesman problem to the 3-SAT problem fairly easily. I'm even going to say that, let's say that there is an n³ time conversion. The idea here, and this could go either way, this is a bidirectional edge. If we could solve the traveling salesman problem, then we could apply this polynomial time conversion algorithm and end up with a solution to this problem, also in polynomial time. So we could find some expensive but polynomial time solution. We would also solve this problem because we have, if we could solve this problem, then we could solve this problem efficiently. And this entire concept grows into a web of algorithms that we have all added to this space. There are edges between any one of these vertices and every other one of these vertices in polynomial time. So if we can find a polynomial time solution to any one of these problems, then we found a polynomial time solution to all of these problems. And that would probably break things because the security of the internet, et cetera, relies on the fact that P is not equal to NP. But every one of these problems also has a non-deterministically polynomial time solution. Yeah.
There's actually a study of security in the possibility of quantum computing where such a thing exists. Like I know SSA has that.
Yeah. So this creates also something that's very interesting with regards to quantum computing. Now, quantum computing is not the same as non-determinism, but the concept of quantum computing does throw a bit of a wrench in this in terms of just how much optimization can we get? Is P equal to NP when we allow for quantum computing? Bit of a different problem, but one that's very much worth checking out and exploring. So non-determinism is useful in terms of the traveling salesman problem is solvable in polynomial time non-deterministically, assuming that you're at a city like Spokane, and there are 5 different cities that we could get to from here. Non-determinism says fork 5 children, send each of those children to each of those different cities. Fork those children for every possible place that we could go from each of those cities. And at the end of all of that, each one of those children would have found some path by the time that child process comes back to Spokane. We would be able to determine how expensive it is to get there. And eventually, every child would have gone to every other city and ended up back in some place that it had been, in which case that process would die. So non-deterministically, it's a relatively easy problem. But of course, non-determinism can't be done with our modern computers. So if we could solve it that way, that'd be great. So this is an open problem in computer science. If you can prove that for any problem that has a non-deterministic polynomial time solution, if it also has a deterministic polynomial time solution, or you could prove otherwise, that that is not necessarily the case. Instant millionaire. It's an open $1 million problem. People have been trying it for decades with no success. As we'll show later on in the class, one of the holes in math is that there are true statements that can never be proven. So it could possibly be that P is not equal to NP, but no proof exists of it. That is very possible. We'll see more about that later, but that's generally why we care about talking about non-determinism, is talking about computer science theory. And as quantum computing starts to become more and more of a reality, a lot of these theoretical concepts start to come into the realm of reality and enter whether there's some way for us to use the theoretical results from non-determinism and applying it to quantum computing. Everything I've already said. Do note that the grammars that you've written for your first assignment and the grammars that we discussed last week have non-determinism built into them via the or that we use. If we say S arrow ASB or lambda, which one do we pick for a particular input if we're trying to determine a particular input? Right now, we have to pick both of them and search both of them. So you're either searching deterministically or you're allowing for non-determinism and say, let's have one child process explore one side, one child process explore the other. Questions on this very theoretical concept? All right, I've talked at you long enough. We ready to build some NFAs? All right, here we go. NFA for the language, a to the n, where n is greater than or equal to 3, union, AB a to the n, a is greater than or equal to 1. First thing I should note, whenever we have exponentiation in our languages, the exponent attaches itself just to the closest character unless there are parentheses. So this is a single AB followed by NAs, not NABAs. So let's see if we can come up with an NFA for that. And feel free to work in groups.
So, and.
What are we celebrating over here?
It's a new laptop. It's my old one.
It's the old fixed one. Got fixed from what happened? You threw it across the room and anchored?
Basically. My backpack was like this in my room and it fell over and see it. That's it? Yeah. And
Oh,
it's
it's
crackable.
Yeah, I remember it being cracked,
Yeah, that's okay.
but it's back now.
Back now.
There is two.
Better than the new laptop.
Sure. It feels right, it's like we 6 stuff.
Sounds like not a very fun argument you have to have.
Yeah, well, I ended up not doing it, I just think, you can learn sorry, so they gave me ordered in, this is 2, 3, and then that can be.
Nice.
And to complete decision.
Definitely, definitely.
The one.
I missed that. What if it breaks again?
I'll do my best to rate you enough in this class. I'm here for you.
And then we have to. Like the house. Minimum 1
An expert in training me for minute.
Personally, I can't really be. Yeah.
Yeah. So I think.
Stop waiting.
2025.
My response to that is, we sell things that will sell.
Yeah.
And I'm like.
Well, I'm trying out
Goodwill?
Yeah,
I see blueberry players to Goodwill.
Yeah.
Yeah.
And you know, so there is no. Because they're part of that one.
It also has to say, is that strange first language?
Like, Matt and I are trying to do an international trip over the first.
Like the language is because of. W is. So and you can call me child and here it's the same thing, so it's N.
You kind of.
And is any number greater than or equal to.
Yeah.
So I think you
Yeah.
So very painful. So I'm just like you have to be
Like, your trips, like, what we go from the ideas.
Have something?
Well, one of the things.
We were going to go to. And I was like, years ago, we didn't have to travel.
Yeah.
And Japan, like, it's $2,000. Like, really the great cheap decisions.
There isn't on the Netflix. There's so like a. Oh, the seashore, right? That's not crazy. I know.
It's like.
Otherwise, second year. First is one day. And it's the day before. So. Oh, I see. Finance.
Like, what am I on space?
It's just. What answers is rated in. So it has. Otherwise, if you had a B and check. Anyway, there's some percentage of. And then more big. More big. Well, yes, so I. Yeah.
Where's your case? Because we have instant rejection.
Oh.
Due to the NFAs, you don't need a total function if you're in a state, and there is no transition out of that state on that character. It doesn't matter whether you're in a final state or not, you instantly reject it. So in your solution, you're in the final state. And you're seeing a B. There's no edge out of that state. It's just that B, so it doesn't matter where we are, because the problem is our reject. So that's not. Correct. Or if you have partial functions. Makes life a little bit easier. Yeah.
Because it's one of your.
I don't think mine's that. I never tried to decide, like, no, that's- My dad was good.
So here is the left-hand side. Do we agree? We need to see at least 3 A's, then any more A's that we see from there. This does not need to be a total function. So we don't need to specify where the B's go. If we see a B in any of these spots, we would just instantly reject. I'm going to try to build the right-hand side of this into the left-hand side diagram to see what modifications, it's not going to be modifications, what additions do we need to make to be able to handle that? Wherever there is a branch from that, I'm going to have a branch in this diagram. So A, B, A to the N, we want to see that first A getting us from Q0 to Q1. That's the first A in the right-hand side. Once we're at that point, we can now see a B, because this is a union, think of it as an OR. So we need the ability to smash these markers, almost time to replace them. We're going to call this Q4. Distinct from Q1, going to Q2 on an A, now we'll go to Q4 on a B. This is the, if we happen to be on the right-hand side, we're going to take that path. And then if we see another A from there, we can accept. And we will continue to see more and more A's, that's fine, as long as we accept, so we can just draw out. It gets us to that accepting state that has the exact same outgoing edge that we want from here. If you follow this path, we have A, B, A to the N. So if we had some string, would we know from the beginning which path we're going to take from the very first A? Let's say I have some string, but the first character I see is an A. We don't know at that point whether we're in the left-hand side or the right-hand side, but it ends up not mattering. There is no forking children in here because we don't have any vertex that takes the same edge and goes to different vertices on that edge label. Once we see an A here, we know that we must be in the left-hand side language. If we see A and B here, we know we must be in the right-hand side language. And that tells us whether we're going to take this top path or this bottom path through this NFA, and all of that is fine. If you had a separate Q5 down here that was kind of a copy of Q3 and did exactly the same thing, that's fine. More states than the optimal solution, but it would still successfully decide this language. Yeah,
AAB.
so kind of what happens if we're here and we see a B? First of all, is there any way it could be any left-hand side or the right-hand side of that language? No. So because we allow for partial functions instead of total functions, we just immediately reject. We're in Q2, there is no outgoing edge on a B. So instead of asking what comes next, etc., we just immediately reject. We are done. It's like we terminated it in a non-final state. If we had AAAB and we were already in a final state when we saw something without an outgoing edge to it, we would still reject. It does not matter where we are when we reject. When we find that there's no outgoing edge, as soon as there is no outgoing edge, terminate, reject. The beauty of a partial function. Excellent question. Excellent overall. How do we feel about this? I think the correct answer is, like, we need another example. here's another example. A to the n such that n is odd. A, B, B, B to the n. Sorry, A, B, B to the n. Again, that's attached to the B. Does an NFA need any trap states? No. No trap states are needed because the entire purpose of a trap state is to have a way to reject. An NFA handles that just by the ability to reject on the spot if there is no such transition.
And the other one gets the route. So you'll have one B, and then if you keep getting B's and rotating on yourself, and zero shows a pattern. Yeah, right. And it doesn't matter where it is. And if only one is, it's still comes. That's all. So because so when you think they won't wait so is all the again and they do for should and it's also to go back Like this much is also just yes, it's super what yeah, but I don't, yeah. You want to.
How are we doing? We need more time to work? We want some more time to work? Think we have a solution? Does anyone want to describe to me their solution? I'm going to see, yeah.
So we have Q0 and on
Zero.
on A, it goes to a vertex called Q odd. And that's a final state. And then we have an edge in A from that Q odd that goes to a Q even state, which is non-final. And then another edge of an A back to the Q odd state.
Okay.
And then from the Q0, we have a B edge. And then we have a final state Q1, and it has to be of a Q or of a B on it. Just a little. And that's fine.
I think this would work if this were B to the end and not B to the end.
Oh, whoops. Could I just add another? Oh,
Yeah, we just need one more state in here, I think. The real question is there any way to combine it with Q odd? Thoughts? Yeah, let's go here.
I was gonna say mine is pretty similar to that, but instead of the B coming from Q0, it's from Q1 or QABB.
Oh, I see.
That one.
Q odd.
Yeah.
The issue here is, can we go to Q even and back and Q even and back and Q even and back and then take that B? And the answer is we don't want to allow for that.
Oh,
So what's tricky about this solution, I think, is trying to figure out whether we can combine certain states or not. So for instance, could we take this Q odd and Q even and make that between Q odd and Q0 instead?
Yeah.
The answer is no, because then there's no way to account for the ABB to the end. Because then we could have B to the end, which we wouldn't otherwise want to do. So yes, we could try to do that, but it would create an issue. Similarly, there's the thought of, well, we could take this A out to Q odd and then branch off and try to make that the ABB to the end. But if we do that, we allow for this loop. So in actuality, this union has to be completely distinct. We need to make that branch at the very beginning and have two separate paths out of Q0 on an A. So now when we see our very first A in the string, you can imagine that there is a string that is accepted by one of these. It could be AAA, it could be ABBB, something like this, doesn't really matter. But you can imagine just looking at the first character of this and trying to decide, given that all we know so far, the rest of this is hidden. We see the A, which one do we take? Now it's ambiguous. As we are parsing the string, we don't know what is to come since we have no look ahead. We don't know what is left of the string. When we see that A, we now must use non-determinism, make two child processes, one of which explores this path, one of which explores this path. One of them is bound to fail. One of them might succeed. And so we will define acceptance in this NFA as if one path, all it takes is one path through this NFA, succeeds, then we accept. So for instance, this AAA, on the A, we're going to non-deterministically fork this process. One of them is going to go here, one of them is going to go here. So there are two processes, one is here, one is here. We see the second A. In this process, we can move to Q even. In this process, there is no outgoing edge from Q1 defined on an A. So because of that, this thread dies immediately. And this thread continues. And is able to go with the final A that moves us back to Q1 where we accept. And we would accept because there was a process that ended in an accepting state. It does not matter that all processes end in an accepting state, or even that all processes end. Some of them will fail early. Does that make sense with regards to this process? We just need a single accepting thread, kind of like the password hacking. We would end up with 62 to the 6th threads active, but one of those would find the password. So that would be good enough. How are we doing? Questions on either of these solutions? How do we feel about NFAs? I do this in most of my classes, as probably most of you know now. Give me a sense of thumbs. I completely understand NFAs and I'm excited to go do them on my homework, or less excited to go do them on my homework, but I think I'd be successful. I understand the basic idea, but I really need more practice before I feel like I can go do this on my own. What is an NFA? Looks like for the most part, we're somewhere in the here to here, here to here. If you want some more practice with this would be an excellent thing to come talk to me about in office hours, because this is what I have for the moment with regards to them. We will be using them for the next thing that we start to talk about. But homework-related questions, great. More practice-related questions, great. See me in office hours. Okay. I hinted at this, but NFAs have an equivalent DFA. You might want to know how to convert between them. Well, you might not care, but it's something that's reasonably important. One thing to note is a DFA is a restricted NFA. It's an NFA, but there are some things that aren't allowed, and there are some things that we have to account for with regards to ensuring a total function. It's reasonably intuitive to go the opposite way, that a DFA has many possible equivalent NFAs. You just have to hide some information about rejection. You could have multiple possible just total to partial function changes. Wherever there is no path through a DFA that leads to acceptance, we just remove that path. So all of those combinations would result in viable NFAs. You could add an unlimited number of lambda transitions to non-final states. Just teleport to this place that is never going to lead to acceptance. Those are all possible NFAs. So there are lots of possible, infinite possible NFAs for any given DFA. But what about the converse? Who remembers the concept of a logical converse from discrete? It was part of, I think, 3 things you studied: the inverse, the converse, and the contrapositive. We start with an if-then, an implication. We have A implies B. What was the inverse?
The inverse.
Inverse was not A implies not B. What was the converse? We don't remember that one as well?
B implies A.
B implies A, yeah. And the contrapositive is the only one we haven't talked about yet. Not B implies not A. All right, so we care here about the converse. So if we say, if we have a DFA, then there is an equivalent NFA. The converse would be, if we have an NFA, there is an equivalent DFA. Is that always true? I've implied that there's at least an algorithm that allows us to convert an NFA to a DFA. Is that algorithm always going to conclude that there is an equivalent DFA? One vote for no. Anyone else? The answer is yes. There is always an equivalent DFA on the other side. Given that knowledge, if I asked you to come up with an algorithm, I'm going to feed you an NFA, return to me an equivalent DFA. What would you have to consider? What would that process look like? Where would you start? Any thoughts on designing that?
I don't know, you need a total function.
Yeah, we need some kind of total function. So thinking about those differences between DFAs and NFAs, how could we eliminate those differences?
Oh, adding for the variable.
Adding potentially more states?
Yeah.
Yeah, it's worth noting that a DFA needs more states than an NFA. Most frequently. That's not always true, but it's almost always true. How many states is the cap? So if I have an NFA with 5 states, what is the ceiling of the number of states that I would need in an equivalent DFA? Any thoughts on that?
The different symbols or letters you have in your language.
It actually does not, which is kind of maybe counterintuitive, but that's intriguing. It would actually have to be embedded within the NFA, so that would scale the number of possible states within the NFA, but once we have an NFA with a certain number of states, that's all that matters. But I like that thought process, yeah.
Would there be no ceiling because that NFA could have any number of transitions out of one?
That's a very interesting way of thinking about it. In terms, there is a ceiling. There is a maximum number of states that we can have. Any guesses as to what that ceiling is in terms of a function? It's actually 2 to the power of the number of states in the NFA. Now that I've said what it is, any guesses as to why? What do they represent? This goes back to our very first day in here. Something mentioned in our very first day when we talked about power sets.
It's like all the possible combinations.
Yes, it is all the possible combinations of states. So if we're reading some characters, and just as we started going through this very last NFA that we created, we forked child processes, and we find that we are in some subset of the states of the NFA. We're going to need, in the worst case, a state for every possible subset of states that we could be in. Once we have that, then we have all of the possible states in a total function of this NFA, all of the possible subset of states that we could be in. So we need to not necessarily add states to the NFA. That's not quite the process we're going to go through, but you can now think of it as we need to find ways to represent all possible subsets of that. Then we need transitions based on the subsets that we could be in, based on the subsets that we could have been in before we read that character. That probably doesn't make a ton of sense, and we are unfortunately out of time. So I'm going to have to come back and fully explain this process tomorrow. But we'll explain it, we'll get some practice with it. It's the hardest thing we've done in here so far. But that is also temporary, because harder things are to come. I have office hours starting now for anyone who would like some help with the homework. or get some extra practice for anything that we have discussed over the last few days.
Sure, sorry.